Okay, welcome to Robotics 1. In today's class, I would like to talk about the differential equations. I would also like to talk about how to do the inverse kinematics on the robot arm. So first and foremost, I want to borrow the robot arm. Can I borrow the robot? Why did you use water? You can use air, no?
It works better with water.
Okay.
It's a lot better.
Okay, so this is the robot arm. This is how it should look like. Now, the first question to all of you is whenever you have a robot arm, the robot arm can look much different in different configurations. For an example, this robot arm is R, R, R. So basically the first three joints are R, R, and R. And this is where this first actuator ends. So, and afterwards, what we have is we have an end effector or the gripper. Now, this robot arm is an RRR manipulator, and at the end, it only has one gripper. This robot arm, what I'm showing you here, again, is RRR, and at the end, it also has an end effector. Whenever you have a robot arm that has more than 3 degrees of freedom, it is very difficult to solve the robot arm in one shot. The way I would solve the robot arm is looking at the first 3 degrees of freedom, and then finally looking at the degrees of freedom that are after the first 3 degrees of freedom. There could be 1 degree of freedom. It could be like a degree of freedom in yaw, or there could be some type of a claw as shown over here, or it could be a spherical wrist. But no matter how the robot arm looks, whether you have the robot arm like this, or whether you have the robot arm like this, first and foremost, we have to draw a kinematic diagram. So first, let's identify the robot arm. So we have to first draw the kinematic diagram. And let me draw the kinematic diagram for this robot arm, and you can tell me if this kinematic diagram makes sense. And then what I have is I have, say, one more. And then probably I have the last actuator. And then here, if you look at it, what I have is I have a gripper. Are you with me so far? Now, next step is assign the coordinate systems. And I'm sure you have done this. So and clearly your coordinate system assignment, yeah.
Since the gripper is just like an open or closed, do we have to include it as a separate revolute joint with the overall rotation?
Let me discuss this step by step. Hold on. So this is the kinematic diagram. This is the first revolute joint. This is the second revolute joint. This is the third revolute joint. And this is the gripper. Now, as rightly pointed out, if you think about it, this last gripper, the objective of this gripper is not to provide any articulation. So what it means is you have the revolute joints, but this position of the gripper is fixed. And these revolute joints, what we have at the end are only clamping it. So basically whatever end effector you have, and if you look at the clamping, so this gripper is going to clamp the object over here. Now there are two things that we need to discuss. The purpose of this gripper is to clamp the object. However, as the orientation changes, so as the first revolute joint, second revolute joint, and third revolute joint, they articulate, the orientation and the position changes. Let me repeat this once again. What's going to happen is, as this gripper is just clamping the object, however, as I rotate the first revolute joint, second revolute joint, and third revolute joint, and imagine if you have an object here, what's going to happen is this object would actually get its orientation and position will get changed. Now, so how do we solve this particular problem? For practical purposes, always, whenever you look at the robot, your actual robot will be different than the kinematic diagram. Now, let me ask you this question. I have this syringe over here, and even though this syringe is sort of a prismatic joint, even though this syringe is kind of a prismatic joint, the final purpose of this prismatic joint is to actuate this gripper. Do you agree with me? Next thing, what I want to tell you is when this gripper is fully actuated position, when this gripper, so this is the open gripper position, and at the end, once you pull this up, this gripper is going to grab the object. Yeah. Yeah, they have to come to class. I try to do this, but then I'm afraid that this will break. And I have to be respectful to all the hard work that he has done. So, I mean, I can try to move this, but then the cables don't reach. I don't know. Okay, so now what I want to do is, so what is the best kinematic approximation for this robot? The best kinematic approximation for this robot is very important. From functionality point of view, this is the first revolute joint, second revolute joint, third revolute joint, and final link length is all the way from this joint, the end of the gripper. So if you want to analyze this robot arm, the way I would do it is I would consider this as an R robot, but finally the final link length would be from this axis all the way where the two arms of the gripper are joined together. Everyone understood this? And this kinematic diagram is actually representative of the actual functionality of the robot. So when you are trying to solve this robot arm should be considered as the projected distance of the gripper, not this distance, but the projected distance of the gripper. Everyone understood this? Yeah. Huh? Can you repeat what you said? Yes. So what you need to do is you need to find, okay, your robot arm looks like this. So what I'm trying to say here is you will have the first revolute joint. The link length for the first revolute joint would be from here to here. Now there is something else I want to talk about. If you look at this actual robot, and you will see this, if you look at this actual robot, understand the revolute joint, the first revolute joint and the second revolute joint, they are not on top of each other. But that is what we approximated in our kinematic diagram. Okay. So what we can do is to perform the actual kinematic diagram analysis, you can consider this joint and this joint to be aligned. So you consider that this joint and this joint be aligned. However, please understand, if you do something like this, your end positions will have a residual offset error, which is in between the first revolute joint and the second revolute joint. Do you understand that or no? In our kinematic diagram, if you consider that this revolute joint and the revolute joint which is here, the revolute joint which is here, because of the way the robot is actually constructed, there is an offset here. Do you agree with me? And you need to take into account the effect of this offset. How would you take that into account, the effect of offset? What would this offset do? This offset is going to add Px and Py from the final end effector position. So you have to compensate for that. If that is not what you want to do, well, then what you can do is you can actually consider perpendicular and parallel, and you can correct that. So when you perform, if you use the kinematic diagram the way I have shown, and that is the reason for actual experimentation, and when you do the experiment, you will see there will be a small error. That small error is not because of the issue in the analysis, it's because of our approximation of the model that we have. Everyone understood this? Did anyone do forward and inverse kinematics and actually got the same results? The results will be slightly off by about 1 or 2 degrees or 3 degrees. But that's okay. Those results are because of the difficulty in manufacturing and then the offsets that we have ignored. So now once you have something like this, believe it or not, I have solved forward and inverse kinematics for this robot. You agree? Can look at the video. As a matter of fact, I have given you the MATLAB codes to do the forward and inverse kinematics of this robot. So from that point onward, it should be super simple. The only issue that you will have is you will notice the answers that you will get from the MATLAB code or the kinematic diagram will not be exact to the answer that you will find using the protractor. And the reason for that is you have these residual offsets, the joint offsets that you're kind of ignoring. You can make it look much nicer because I want you to think about it. The joint offset is sort of a constant link length that will be present in every forward and inverse kinematics. So what you can do is you can just subtract that joint offset from the end effector position and you should be good. But other than that, this actually looks very nice. If you really want, you can make it a little bit nicer. What I would do is I would actually add a washer here and then basically use the super glue and glue that washer over here. You can do the exact same things over here. But other than that, it looks beautiful. It is very nice. Now, some of you are really hardcore robotics. I actually just make this a little bit nicer because what you want to make sure is that this link length and this link length is the same. Otherwise, it will grip something like this. It won't grip, and our assumption will be wrong. You really don't need water, but if you want to use what I thought air would also work. But if you really want to use some hydraulic fluid or water, that's totally fine. One additional thing, it's not part of the assignment, but what I want you to think about is you can actually create this model inside the SolidWorks or import this model in the SolidWorks and then basically have the SimScape or Sim Mechanics create an XML file and interface that with MATLAB. if you do it, if you send me the file, and I just don't want to spend time on it. If you send me the file, the XML file or the SimScape or Sim Mechanics model, I will show you how you can use the MATLAB script that we created in class, put it inside the Simulink, and then actually you will see your robot arm doing exactly what you want to do. So if you want me to talk about it, just send me your SimScape files. It's very easy. What you need to do is download the add-on from MathWorks. It will plug into SolidWorks, and then it will spit an XML file that you can actually import in MATLAB. And it will maintain all the dynamic properties, the link constraints, and everything. So it's a lot of fun. The other thing which I want to talk about is you can actually add simple servos. Remember the servos that we used, and actually have this robot arm perform a mechanical actuation based on those servos. So you can actually have a fully functional robot arm that you can control using a microcontroller on an Arduino. So, but this is good. Any questions on the assignment?
Yes.
Yes.
So in the inverse kinematics, you asked that given the position and orientation, find the inverse kinematic joint angles.
Mhm.
And when we've done the previous like RRR, we just looked at the position equations and solved those for the inverse kinematics. How do we factor orientation into that?
Okay.
Kind of going off of what you just asked.
Yeah.
So I tried to approach with like Euler angles where they would input that. Would I restrict it and only allow them to pick like 2 out of the 3 Euler angles because it can't rotate about a certain axis? So it's
Okay. Now I have to answer this question a little bit more detail, because that is super duper important. Consider, and that is a very practical problem that you'll face in robotics. So this robot is an R robot. So first R is perpendicular to second R, and second R is parallel to third R. Corresponding to each revolute joint, I have a theta, theta 1, theta 2, and theta 3. Do you agree with me? Once you solve the forward kinematics equation, you are going to have a px, py, and pz. And px will be the function of theta 1, theta 2, theta 3. Py would be another function of theta 1, theta 2, theta 3. And pz would be another function of theta 1, theta 2, theta 3. Once you solve the inverse kinematics for the given value of px, py, and pz, you are going to get the value of theta 1, you are going to get the value of theta 2, you are going to get the value of theta 3. Do you agree with me? Here is what it means. If I give you a px, py, pz, to find out the value of theta 1, theta 2, and theta 3, and because this is a 3 degree of freedom robot, your end effector orientation is fixed. What that means is very important. So this, once you have theta 1, theta 2, and theta 3, you will substitute these values of theta 1, theta 2, and theta 3 in 0, R3. And 0, R3 is gonna give you a 9 3x3 matrix. Okay, is gonna give you a 3x3 matrix. And then I just want to, I didn't discuss this, but this is very important. I would like to discuss this. I want you to go to MATLAB. I want you to go to MATLAB. I want to go to MATLAB. And there is MATLAB Euler to rod. So can you, online students, can you see my screen?
Yes,
Online students, can you see my screen?
yes, Professor.
Okay. So what I want you to do is, there are two important commands that I want you to remember. And I will tell you the difference. The first command is UL to ROTM. So wherein, if you supply roll, pitch, and yaw angles, roll, pitch, and yaw angles, it will give you a rotation matrix. But in this particular case, from the joint angles, we have found out this rotation matrix. So the command is ROTM to EUL. So the command is ROTM to EUL. So whatever you get here, whatever you get as 0R3, you will take that 0R3 and substitute in this command, which is ROTM to EUL, and you supply the rotation matrix, and it will give you the Euler angles. Are you with me so far? Now, let me answer. I think a student asked me about inverse kinematics. So let me answer the question. So when he asked me, how do we do inverse kinematics? So I said, to do the inverse kinematics, either you can use end effector position or you can use end effector orientation. You won't be able to get both and then try to satisfy the conditions, because you have only 3 unknowns. To solve for those 3 unknowns, you need 3 equations. Everyone understood this? So you can get θ1, θ2, and θ3 either from Px, Py, Pz, or you can get θ1, θ2, and θ3 based on Euler angles or rotation matrices. Everyone understood this? Both ways is fine. So you can do inverse kinematics either based on Px, Py, Pz's, or you can do inverse kinematics using the orientation matrix. Everyone understood this? And I actually solved. So if I, okay, for my own satisfaction, I need to clarify this. So imagine you got θ1, θ2, and θ. This is the problem. I will have to switch to explain. But let me, before I go on to the whiteboard, there's something I want to talk about. This command, basically, there are 3 rotation sequences. So basically, rotation about X, rotation about Y, and rotation about Z. These rotations, please remember, these rotations are always about the inner shell or fixed frame, which means the roll, pitch, and yaw. These are called Euler rotations, Euler angles. They are always with respect to the fixed coordinate frame, not moving, fixed. Do you agree with me? And depending upon, this is the perfect time for a demonstration, depending upon the sequence of orientation. Check this out. So sequence of orientation, rotation about X, rotation about Z. Check this out. Rotation about X, rotation about Z is different than rotation about Z and rotation about X, which means the sequence of rotation is super duper important. So that's why I talked about it in my earlier lesson, that there are 12 combinations of Euler angles. And if you use rot m to EUL in the parentheses ROTM. This is what I recommend. It will give you Z, Y, X rotation. Are you with me? Z, Y, X rotation, and this is the rotation is usually used by default. So Z is yaw, X is Y is roll, and Z is pitch. If you use a different orientation sequence for some reason in aircraft mechanics, you have to use some different orientation sequence. So you can specify the rotation matrix, and then you can specify the sequence, and it will give you the Euler angles in that particular sequence. Everyone understood this? So please take a look at, and this actually explains very nicely. And here I would strongly encourage you to look at these examples. And then this actually is very, very important from a solution point of view. Everyone understood? So if you are given Px, Py, Pz, substitute Px, substitute Py, substitute Pz, and get the values of theta1, theta2, and theta3. As theta1, theta2, and theta3 are known, substitute theta1, theta2, theta3 in the rotation matrix 0, R3, and you will get the final orientation matrix. Do you agree with me? Once you get that orientation matrix, plug it in here and you will get Euler angles. Why Euler angles? Once you see the rotation matrix, it's very difficult to visualize. But as soon as you see the Euler angles, you can say, hey, 90-degree or 30-degree pitch, 20-degree yaw, and maybe 30-degree roll. So it's very easy to visualize. Looking at the rotation matrix, it's very difficult for us to see the orientation or get a feel for the orientation. Same thing with Cottonian. Understanding the physical interpretation of Cottonian, it's a hyperplane, it's difficult. That's why for understanding purposes, for visualization purposes, we use roll, pitch, and yaw. Everyone understood this? But there are 12 combinations of roll, pitch, and yaw possible. Out of that, we are going to use only one, and that we will use consistently in our analysis. Because if your roll, pitch, and yaw is different than my roll, pitch, and yaw, our orientations are not going to be the same. If our sequences are not the same, answers won't be the same. Everyone understood this? Question? There was a question here. Somebody raised a hand. Question? Okay. Yeah.
So once we get those roll, pitch, and yaws in the rotation matrix, we just compare those against input to see if that position is achievable.
No, you will, if I give you positions, you will get theta1, theta2, theta3, and will tell me for these theta1, theta2, and theta3, this is the orientation you get. And that's all.
Because the assignment question asks given position and orientation.
Oh, so position will give you, okay, you're right. Given the position, you will get one solution. Given orientation, you will get another solution.
So we solve for position and we see if the resulting orientation.
It will not be the same. Let me explain what. So, okay, everyone understood this? Okay. Now I need to go back to my whiteboard, and I will explain what the question is asking you. Okay. So what is this question asking you? So if you look at that question, it is asking you, given the orientation and position, find out the inverse kinematics. Now, if you find out Px, if you are given Px, Py, and Pz, you will find theta1, theta2, and theta3. Once you find, substitute this theta1, theta2, and theta3 in the orientation matrix that you got, you will use rot m to Euler, and then give me a roll, pitch, and yaw. Because of the way the robot is configured, you cannot control orientation and the position at the same time. Okay. Now here is the alternate computation. Alternatively, suppose if I give you end effector orientation, EE orientation, and I specify, or you specify, the end effector orientation is maybe roll is equal to 20 degrees, pitch is equal to 30 degrees, and yaw is equal to say 70 degrees. Then clearly at this point, you have to specify the sequence. And assuming our sequence is Z, Y, and X, then what you will do is, for this roll, pitch, and yaw, you would find out a 3x3 matrix. And this matrix would be an orthonormal matrix. So there will be numbers here. So numbers like 0.1, 0.2, whatever, there will be numbers. Now, once you perform the forward kinematics, remember, you always have 0R3 in a closed form. Are you with me? This 0R3 will be function of theta 1, theta 2, and theta 3. So you will have 0R3 as theta 1, theta 2, and theta 3. Now what you should do is, you should equate this to this 0R3, which is a big function of theta 1, theta 2, theta 3. And what you should do is, you should select the terms. You just have to select 3 terms that would allow you to compute theta 1, theta 2, and theta 3, just like spherical wrist. Are you with me so far? So basically, you may say, oh, this is 0.1. Here there is a term which comprises of sines and cosines. Here there is a term that comprises just of theta 3. And maybe here there is a term that comprises of theta 2 and theta 3. So just select 3 equations and you will get 3 unknowns. Now what happens next? Once you get theta 1, theta 2, and theta 3 from the orientation sequence, you will substitute them in the Px, Py, and Pz equations. And they will give you some value of Px, Py, and Pz. So this problem, the way we have solved it is, you cannot simultaneously satisfy the position and orientation. It may be satisfied, but in general, it's not possible. So given the position, you can find out theta 1, theta 2, theta 3. Given the orientation, you can find theta 1, theta 2, or theta 3. And that is precisely the reason that we add a spherical wrist at the end. Everyone understood this? Any other questions? Now, I just want to take another example. Is imagine if you have a robot arm, something like this. So in this robot arm, what you have is, this is your end effector position, and here you have a revolute joint that you can independently control. How would you solve this problem? This problem would be solved as if, this problem will be solved as if you have an R, 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 and here the spherical wrist, but the last 2 joints of the spherical wrist are 0. Are you with me so far? And you will get the answer. Once again, I repeat. If you have a robot arm, something like this, where at the end there is a revolute joint that is independently controlled, and that can change the orientation of the end effector, not the position, but the orientation. And what you will do is, you will solve this problem just like the spherical wrist here, but in the spherical wrist, last 2 joints theta 4 and theta 5 and theta 6 will be equated to 0. Everyone understood this? And then you should be able to solve this type of robot. Okay. I spent a lot of time discussing, but I'm gonna give you all. Oh, you are not able to do this equation for theta from px, py, pz. I think I have given the solution for this MATLAB script that works, right?
So what happens if you're trying to solve, like, for example, for a base condition outside the workspace of the robot?
Okay, then you will get an error. Now, next question is, how do you have the joint limits? Now, first and foremost, please understand our kinematic diagram is different than the robot is physically realized. So what it means is, even though I'm assuming the robot arm to be horizontal for kinematic purposes, the actual robot arm may not be horizontal. So depending upon the geometry, depending upon the constraints, every joint has particular limits. So for an example, because of the servo here, it cannot do 360 degrees, but it can, the first theta 1 can go within certain joints. Theta 2 can go from here to here. Theta 3, as you can see, can go from different joints. These theta 1, theta 2, and theta 3 are the joint variables. So which means what we should do is follow the consistent coordinate system. Whether your z-axis is coming out this way or that way, that's totally fine. And find out physically what are the possible angles, minimum and maximum. Find what are the minimum and maximum angles. There's something else that I want to talk about. Okay, before I go further. Everyone understood that the robot has some joints physically certain possible. Everyone understands this? Now here comes the tricky part, and I want you to understand this. Imagine in this particular configuration, the orientation can go like this. Do you agree with me? But as soon as I change the orientation of this joint, I get more articulation. What that means, and this is very important, and this is what I want you to think about, that depending upon the orientation of the second joint, you can have a different articulation of the third joint. Which means, if here is how you would do it. If, and it's very easy to do in SolidWorks, but you can do it manually. So for an example, this is your theta 1, this is your theta 2. If your theta 2 is at theta min, if your theta 2 is at theta min, theta 3 will be like this. This is the value. If your theta 2 is slightly greater than theta min, then you got a different orientation. If theta 2 is at some other angle, then you got the different articulations. So what you should do is very important, that you should be able to articulate the positions in your if and then statements. When you are checking, make sure you have the condition on theta 3 that depends upon theta 2. Some of you may ask me, how would I do it? Once you actually find out some in Excel sheet, once you find out what is the value of theta 2, what are the possible limits for theta 3, what is the value of theta 2, what are the possible limits for theta 3, and once you find that, it's very easy to come up with some sort of a regression model that will give you those answers. That is exactly how you would solve a practical robot arm. Because what may happen is you will realize that maybe you can't reach this for certain values of theta 2, but for different values of theta 2, you can reach the position that you want in the workspace. Everyone understood this? There is a lot to it than that project, than what we see.
Can't you plot a graph, 3D graph?
You can do any graph, you can come up with a regression equation, or you come up with a lookup table, whatever you want to do, that's totally fine. So that will give you the possible constraints. Okay, any other questions?
And how long is the extension? for these?
How much do you want? Next week will be spring fall break. So clearly. Okay, I'll give you an extension of 1 week. So next Wednesday. Yeah, not this Wednesday. Clearly, if I say next Monday, you're gonna say, oh, fall break, you can't do it. Any other questions?
He wants to bring the physical arm in.
No, you can just add a picture,
Okay.
but then make sure that you have your name or everything written on the robot arm everywhere. Okay, because if the grader sees that, hey, your robot arm looks dangerously similar to somebody else's, the grader will ask you and that person to bring 2 robot arms. That has happened to me before. So this is an individual assignment. Now, if you are just, okay, if you think that, hey, I just don't have time, and if you want to spend money, you can get a robot arm from Amazon as a kit for about $12. Pre-cut robot arm for $12. So if you want, that's fine too, but your forward and inverse kinematics will be slightly different. Okay, spent a lot of time. Any questions from online students? On paper, we have to get equation. Yes, on paper, we have to get equations for theta. And then you have to use the MATLAB code that I explained in the class to solve the inverse kinematics. And then you have to look at the code. You have to look at the code for the inverse kinematics based on the orientation. Okay, everyone clear about the assignment? Okay, now what I want to do is, I don't think I will be able to finish, but I just want to get started on the differential equation. So solving differential equation. So remember, all our differential equations that we encounter, they come from one or the other form of conservation laws. So for an example, summation of forces is equal to mass times acceleration. This can be written as a differential equation. So for an example, if the external force is constant, the mass is constant, acceleration is expressed as x double dot. So what you have is, you have 1 is equal to x double dot, or better yet, x double dot is equal to 1. So this is a differential equation. Differential equation has 2 derivatives. So to solve this differential equation, what we need to do is, we need to perform integration 2 times. So if I integrate this for the first time, so I need to integrate x double dot with respect to t 1 dt, and then I get x dot is equal to t, and with a constant of integration c. This constant of integration talks about the initial condition when time t is equal to 0. So which is c, I'll call it c1, is initial velocity. If I want to find out the displacement, I perform integration 1 more time, and then I get t square by 2 plus c1 times t plus c2. And now I got a nice expression. Please note, this expression is function of t. And on the left hand side, I have x, which is function of t. So what I have is, I have the solution of the differential equation. Solution of differential equation for a linear differential equation is obtained using integration. If you have one dot, you have to integrate it once. If you have two dots, you have to integrate it twice. For linear differential equations with constant coefficients, once again, for linear differential equations with constant coefficients, these equations are of the form, say 5x double dot plus 3x dot plus 1 is equal to 0. Or this could be like maybe 3x triple dot plus 1 is equal to 0. Wherein these coefficients, which means the thing that multiplies x dot or x, they are constant. They are different than the linear differential equation with varying coefficient. So here, what you're going to have is, you're going to have maybe sine t x double dot plus cosine t x dot plus 1 is equal to 0. So now what you have is, you have a differential equation that is actually time varying in nature. It's not fixed, but it is time varying. These equations, they are not discussed in your differential equation class. In your differential equation class, these are the type of equations that are typically discussed. Unless you're a hardcore mathematician or applied mathematician, you will not solve these equations in a closed form by hand. You would always use some type of numerical solver like ODE 45, ODE 23, or Mathematica solver, or some special functions to solve these equations of this type. So in this class, or as a matter of fact, in your once you become a professional engineer and you're solving on problem, there are very few differential equations that can be solved by hand. For most of the differential equations, whether they are time varying, time periodic, time quasi-periodic, or non-linear, you would resort to a numerical solver like MATLAB, Mathematica, Maple, or something like that. But the good news is, there is only one technique that you need to remember to solve linear differential equations with constant coefficient. There is only one technique that you need to remember. Now, and this technique comes from the fact that, please understand, when we had a differential equation, we just integrated it twice. And at the end, I want you to understand this concept very, very carefully. At the end, we got this expression. What does that mean? It means I can substitute the value of t and get the value of x. So I can plot on x-axis, on horizontal axis t, and on vertical axis value of x. So I have some sort of a relationship, a mathematical relationship between the independent variable, which is on x-axis, and the dependent variable that is on y-axis. Everyone understood this? At the end of the day, all these mathematics and expressions are great. But what does that mean? This is what it means. If I take this expression, x is equal to something, differentiate it once, I would get the expression for x dot. Do you agree with me? Then I redifferentiate that expression for x dot. I will get the expression for x double dot. Do you agree with me? Now, if I substitute that x double dot that I got in the original equation I started with, my left hand side would be equal to my right hand side. This is a very simple concept, but I want you to understand this. How do engineers solve the problem? Most of the problems engineers solve by trial and error. What that means is if I got infinite resources, I can assume the functions, maybe million or billion functions, plug those functions in that expression, and as soon as my left hand side is equal to my right hand side, that is the solution. Do you agree with me? And that is the technique that is most widely used. What do I mean by that? What I want to do is, I want to solve one simple problem using the conventional technique that you studied in differential equations class. And then I want you to think about the same problem using a general function that satisfies the equation. And then that approach can be used for any differential equation. So please try to understand. So as an example, and this concept is very important because this would relate to the eigenvalues, this would relate to the stability, this will relate to the short-term and long-term behavior of the system. So please pay attention. I'm going to solve this expression, and let me say this expression is x dot is equal to maybe say 5. X dot is equal to 5. Or what I want to do is x dot is equal to maybe a. I want to solve this equation like this. If I want to solve this expression, what I want to do is I will have to rewrite this expression dx by dt, and there is a reason I have a number here, and I'll tell you this in just a bit, is equal to a. Then what I need to do is I need to write separation of variable dx is equal to a times dt. Do you agree with me? Then since there is only one dot, how many times do I have to integrate? Once. So I'm going to integrate the left hand side and the right hand side. And what do I get? I get x over here. A is a constant that comes out of this expression, and this dt gives me t. But since I have integrated it once, let's not forget the constant of integration, and I'm going to call this c. So this expression is going to give me something like x, and if I plot t over here, this c starts for the initial condition, and then as you can see that this a, this is going to be the relationship between the x and t. Are you with me so far? Now what I want to do is I want to solve this problem something like a slight variation. So consider that this problem is dx by dt is equal to x. Now what that means is I have an expression x dot is equal to x, where x dot is dx over dt and x is x. I'm going to follow the exact same procedure what I have done on the right hand side, and I will write this expression as dx by dt is equal to x. Next step is I need to separate the variables. Dx over x is equal to dt. Now I need to integrate the expression on both sides. After integration, dx over x, what is the integration of it? Ln x, natural log of x. And this becomes dt becomes t. Dt becomes t. And then I get an expression of c. Do you agree with me? To get rid of logarithm, I will have to use the exponent. Take the exponent on the left hand side, take the exponent on the right hand side. Left hand side, right hand side. Exponent of the natural log. Exponent of a natural log is the variable itself. And this is going to become e to the t, e to the c. Do you agree with me? C is a constant. E to the c. So e to the c is a constant. I'm going to call this as a. So what that means is x of t is going to become a e to the t. Are you with me so far? So just like the previous case, if I decide to draw the relationship between x of t, which is the dependent variable, and t, which is the independent variable, I want you to understand the most important part. And everyone pay attention, because this is going to give you the relationship between the stability, system behavior, and eigenvalues. So I want you to understand what's happening here. Everyone understood that x dot is equal to x is a differential equation. This is the first order linear differential equation. Why is this a first order linear differential equation? Because this equation can be written as x dot is minus x is equal to 0. So this is the first order linear differential equation with constant coefficient. I performed the integration once and I got the expression, and this expression involves an exponential term and a constant. Are you with me? This equation involves an exponential term and a constant. This constant is an indication of initial condition. So for example, if my x at time t is equal to 0 is 5. Let's say so at time t is equal to 0, at t is equal to 0, x of 0 is equal to 5. That means x at t is equal to 0, e to the power 0 is 1, 5. Which means, do you agree with me, the value of a is equal to 5? Are you with me so far? So which means at time t is equal to 0, at time t is equal to 0, I'm going to start with 5. Now what happens next? If as time t goes on increasing, time is not decreasing, time goes on increasing, can you see that this constant a will get multiplied by this exponential rise function? Are you with me? Look at that. That previous function was a linearly increasing function. But since here I have an exponential function, this would go up exponentially. So this is how that function would look like. Are you with me so far? Are you with me so far? Now, what I want you to observe is, check this out. Here, there is 1 that I did not write. And here, that 1 popped up. What that means, and this is very important, if I have an expression x dot is equal to 0, if I have an expression x dot is equal to 0, do you agree with me? X of t would be a. Does everyone agree with me? What that means is now, since my a is greater than 0, I got an exponential rise in the solution. If my a is 0, I will get a constant solution. And what happens if my a is negative? If my a is negative, then it will be something like this. And I want to explain this. So think about it. X dot is equal to ax, dx over dt is equal to ax. That gives rise to dx divided by x is equal to a dt. Integrate both sides. Ln of x is equal to a is a constant times t. Taking log on both sides. So e, what I get here is I get x of t is equal to a e raised to so at, so e raised to at plus c. Just a second. It will be at plus c e, and x of t is equal to e to the at times e to the c. E to the c is a constant. I'm going to call this a is a constant, e raised to at. And this is the most important expression that I want you to remember. So a linear differential equation with constant coefficient will always have a solution that contains the exponential term. Linear differential equation with constant coefficient will always have a solution that contains exponential terms. In this particular example, let's imagine a case if a value is greater than 0, and then what's going to happen is the system response, if a value is greater than 0, if a value is more than 0, the system response would be exponentially increasing. If a value is 0, then the system response will be flat and horizontal. If a value is less than 0, then the system response would decay. Are you with me? In other words, system could be unstable if a is greater than 0. System would be simply stable if a is equal to 0, or system could be asymptotically stable if a is less than 0. Are you with me so far? What do I mean? What is the definition of stability? Simply stable means the system is going to stay where it is. So that's what is indicated by this horizontal line. System is going to stay. Its energy is not going to increase. Its energy is not going to decrease. What do I mean by unstable system? Unstable system means the system response would increase. And what do I mean by asymptotically stable? Asymptotically stable means the system response would decrease. And here is a typical figure that you have a marble on a surface. So if you actually perturb this, then the response would increase. You have a marble on a flat surface. If you perturb it, it's going to remain flat. And then you have a marble in the bowl. And then if you perturb it, it will finally go back to the initial position that you started. Everyone understood this? Everyone really understood this? What was the first one? First one is unstable. This is simply stable. And this is asymptotically stable. It will never come back to its original position. So can you see that in the very first case, you start with 5, you are never going to come back to 5. In the second case, if you start at 5, you will stay at 5. And in the third case, if you start at 5, you will go down and finally you would go to 0. Everyone understood this? Now here comes the important part. This equation is a scalar equation. This equation is a scalar equation, which means the expression reads like x dot is equal to a number times x. Everyone understood this? This is not a matrix equation. This is not a matrix equation. However, you would observe the exact same phenomenon in the matrix equation where the value of A, that A which is constant here, that is clearly given to us, will be nothing but the eigenvalue of that matrix. So for an example, if you have a differential equation, and I will explain this again in the next class. If you have a differential equation that has multiple rows, not just one row, with 2 or 3 rows, and you formulate that differential equation as a matrix differential equation, where you have the derivatives on one side, you have a matrix and multiplied by a vector, then the eigenvalues of that matrix will dictate whether the system is unstable, asymptotically stable, or simply stable. Everyone understood this? And whatever we have done here, you would use the exact same approach to solve a linear differential equation with constant coefficient. As a matter of fact, you can use the exact same approach to solve a linear differential equation with constant coefficient that has an external forcing, and it will give you the same answers. I'm going to stop here, and in next class, I will take some concrete examples, but here is how I'm going to solve a differential equation. I'm going to assume that the differential equation has a solution of the form a e to the at. Every differential equation, the linear differential equation with constant coefficient, has a solution of the form a e to the at. Substitute this differential equation, substitute this assumed solution of the differential equation in the equation, and compare the left hand side and right hand side. If my left hand side is equal to my right hand side, boom, that is the solution of my differential equation. That is the gist of your differential equation class. What is the gist of the differential equation class? If you are given a differential equation and it's a linear differential equation with constant coefficient, you would assume the solution with 2 unknowns, a and a. Plug this solution into the differential equation. If it has velocity, which is if it has x dot, take the derivative, substitute that. If it has acceleration, take second derivative, substitute that. And then finally, at the end, compare the left hand side is equal to right hand side and find the value of a. Once you know the value of a that satisfies the differential equation, the left hand side is equal to right hand side, boom, that is the solution of the differential equation. And if you cannot solve the differential equation using the technique that I told you, the next logical step is using MATLAB, because you won't be able to solve that differential equation by hand, most likely. All right, I'm going to stop here, and I will actually work out some problems next class.